We've just learned that the very smallest possible stars are red dwarfs, and these exist in a mass range of about 0.08 to zero point 0.4 solar masses. The unique characteristic of red dwarfs is that they are convective all the way through, from the core out to the outer surface. And so they cycle the hydrogen into the core, and the helium that's produced in the ashes of hydrogen fusion are cycled back to the rest of the star again. So because of all this cycling, all the hydrogen is converted into helium. Now, the core temperature of red dwarfs is low, thus their fusion rate is low. And because of that, they last for a long time, hundreds of billions, if not trillions of years. In fact, any red dwarf that's been produced in the universe is still burning because there hasn't been enough time to convert all its hydrogen into helium. Once it is converted into helium, however, that's it. It's the end of the story for a red dwarf because it never gets hot enough in the core to fuse helium. So you get a big ball of helium. That's the end result of a red dwarf, which again, we don't see any of those because there hasn't been enough time. But it will just dim and move off to the lower right-hand side of the HR diagram. Interesting piece of information regarding these particular stars is that they would not make a good candidate for the support of advanced life on a planet. So any planet that's orbiting a red dwarf, for it to be in the liquid water habitable zone, it's got to be close enough to that dwarf that the tidal interaction would be so extreme that it would tidally lock the planet to the star, which of course, if you remember, means that one side, one face of the planet would be pointing toward the red dwarf all the time. And that would, again, not be at all conducive to producing conditions where advanced beings could evolve, if even any kind of life at all. So we would not tend to want to spend a lot of our resources looking to red dwarfs for alien life. Recent studies have shown that many of the stars, more of the stars than we thought that are in the galaxy, are probably isolated red dwarfs, not in binary systems. So even though there are a lot of binaries, it looks like the proportion of stars has shifted over to being isolated red dwarfs in our galaxy and other galaxies as well. Let's discuss main sequence evolution for stars that we're more interested in, that would include our sun, for instance. So we're talking about stars that are in the range of masses from 0.4 to 2 solar masses, so just out of the red dwarf phase. And this diagram shows the progression on the HR diagram of a star like our sun, a 1 solar mass star, over a period of about 1 billion years, where it's leaving the main sequence and progressing toward becoming a red giant. So as the hydrogen fuses into helium, the number of particles drops in the fusion process, hydrogen into helium, and therefore it takes less space for the same amount of mass. So the core is contracting, and in that contracting, it's heating up as gravity crushes it all the more. Well, if you're heating up the core, then the fusion rate increases as well, and therefore the luminosity goes up. So the rate at which energy is being produced is actually greater. And in about 10 billion years, a star like the sun moves across the main sequence. It takes 10 billion years to travel across there, and what's really happening, we're going vertically, so what's changing is the luminosity. The luminosity is changing, not really the temperature, even though relative sizes are changing here. Well, if the temperature stays the same, then to be more luminous just means it has to be increasing in size, that's all. So that all makes sense. Now eventually the hydrogen is essentially depleted in the core. So the fusion ceases, and therefore the internal pressure from the nuclear explosions going on in the core have ceased, and so gravity that's trying to crush the core now really gets a grip. It really has the ability to crush it down because there's nothing to hold it back that that fusion process in the core is no longer trying to keep it from being crushed by gravity. Therefore, the condensation, the compression, and the size of the core is greatly diminished. Well, the core size is diminished and heats up all the more. And so as that happens, we have the path going off to the right here. And you'll notice the luminosity is staying about the same. Well, the reason for that is as the core heats up, it pushes the outer layers out. So it's making the sun bigger. But as it does that, those layers cool at the same time because they're expanding. So it keeps the luminosity about the same. This whole process is about 1 billion years. And in that amount of time, the sun becomes a red giant, actually becoming about 100 times bigger. Notice that we're progressing along different radii lines here. So it's becoming larger, about 2,000 times brighter than it was when it was on the main sequence. So let's investigate a little more detail why this happens. So what's happening in this process is totally controlled by what's going on in the core. Remember, the core becomes the ashes of the hydrogen fusion, which is helium. And here's a graphic showing the sun with a hydrogen burning core, and that's a normal main sequence star. The fresh hydrogen actually produces a shell around the core, and here's a shell of hydrogen around the shrinking core. And as that core heats up, the shell starts to fuse hydrogen, and it's producing the main part of the energy that is providing the luminosity of the sun. It's called hydrogen shell burning. So the shrinking helium core shrinks this shell also, and in this whole process the fusion rate increases. So even though it's getting smaller, it's getting hotter and actually producing more energy. So this builds thermal pressure, pushing the outer layers outward, and the sun grows and grows until the luminosity balances the fusion rate inside. So the entire outer surface will be in balance with that internal fusion rate. And it's actually expanding into becoming a red giant, which has got a cooler surface, but a lot more surface area. So in this way, the sun becomes a giant star. Most of the mass is deep inside in that small core. And the key thing is that the normal self-regulating process, where before, when you had fusion going on in the core, any increase in fusion rate of the core itself would cause the core to increase in size and cool off, and therefore decrease the fusion rate, so it's all in balance. Now, because the core is inert, it shrinks down, heats up, and there's nothing to balance the internal heat. I should say nothing to balance the crush of gravity, because there is not an increased burning rate inside the core itself, because it's done, it's used up its fuel. So the core cannot be inflated. The helium ash from the shell is continued to be fed to the core, amplifying the process. And the core eventually rises to 100 million Kelvin, and at that temperature, the helium finally ignites. So we'll continue that story in a couple of minutes. So, just to give you some perspective on the scale of red giants, here's an image in the cluster M50, and there's a few red giants that are shown in this particular open cluster of stars. Well, the red giant indeed deserves its name. Take a look at the size of our sun in the normal main sequence. Here it's shown in larger view. About 1/100th of an astronomical unit in diameter, whereas when it blows up into a red giant, it literally becomes about a whole astronomical unit in diameter. You can see just by the curvature here how much bigger it is than our sun. Keep in mind, as huge as that is, it seems like it dwarfs the sun. Well, it does dwarf it in size, but, well, it's still the same star, isn't it? I mean, it hasn't gained any mass. So the mass that is contained in the sun now is distributed throughout this whole huge volume. So you can imagine that the layers of gas are very tenuous, very thin, but it at the same time has a teeny weeny teensy core that is actually denser than the core of the sun was before it became a red giant. Well, I've been talking about how the inert helium core gets crushed by gravity, and there's no internal fusion in the core to resist gravity. So you might be wondering, well, exactly how does the core stop from being fully crushed? The fact is, the thermal pressure that's in the core is too low to resist gravity. And so it would continue to crush down, except we have a new kind of pressure called degeneracy pressure that now comes to the rescue. So what is degeneracy pressure? Well, in normal thermal situations, as you compress, you increase the temperature, and that increases the pressure, and so it comes into balance. However, we have a phenomena now where things are crushed so much that we run into the quantum mechanical effect known as the Pauli exclusion principle, namely that no two quantum particles can exist in the same state. So what this translates into is these electrons that are being crowded more and more as a result of this compression. Note that the compression heats the core up enough to where the atoms are ionized. So whether they're ionized or not, though, electrons can only be shoved so close together. They can only exist in certain energy levels. When those energy levels are filled, more electrons can't come into the same levels. So that's the source of the problem here. All the lower energy and then higher and higher energy levels are being filled as this goes on. So the electrons that have been stripped from the atoms cannot all exist in the same place, like in a crystalline structure almost, between the nuclei, because of this Pauli exclusion principle, the quantum effect where the particles cannot exist in the same state. What has to happen is that as it's crushed, the electrons have only one choice. They have to jump to higher energy levels. They can only speed up, and that is extremely difficult to do. The compression has to boost the energy levels, and that makes the material almost incompressible. And in fact, it is the type of incompressibility that keeps gravity from continuing to crush the core down. It's a degenerate core, it's called. It's a very strange form of matter where the pressure no longer depends on the temperature like normal matter, but it all has to do with the density, how close these particles are to each other, how close they're being squeezed together, which then causes the temperature will go up, but the increasing temperature doesn't increase the pressure. It's the density itself. So it's all a little bit strange and not normal to your everyday experience, of course. So the core is not only incompressible, I put that in quotes because everything has its limits, as we'll find out, but also it cannot expand and cool when heated, so the normal thermostat isn't working. Therefore, the temperature can go up like crazy because increasing the temperature isn't going to expand the core and cool it down. So that has a very dramatic effect on the subsequent evolution of our sun at this point. So now back to our story. Remember how the contracting helium core has risen all the way up to a temperature of 100 million Kelvin? Well, it's at that point. The helium nuclei are moving so fast at those temperatures that they have the ability to get close enough for the strong nuclear force to grab a hold of them, and they fuse in what's known as the triple alpha process, where 3 helium nuclei fuse together to form a carbon plus energy. Actually, it turns out that 2 helium nuclei fuse and into beryllium, which is stable for about 1/100 millionth of a second, and in that short amount of time, a 3rd helium nuclei fuses with that. In any case, it produces carbon and energy according to E is equal to mc squared. just like the regular hydrogen fusion process, but it's quite a bit of energy released here with each gamma ray photon. So as we already just discussed, in stars like the sun, the thermal pressure is insufficient to halt the contraction of the core from the onslaught of gravity until that degeneracy pressure kicks in and stops it. But now the helium fusion that's going on, which is very dramatic, heats the core rapidly. But as the core heats, remember it's a degenerate core, so it doesn't expand. The pressure does not increase as a result of the increase in the temperature. And so for a few hours, the core temperature and the fusion rate are rapidly rising. And this process is the very dramatic effect known as the helium flash. And during the helium flash, in just these few hours, the temperature is going from 100 million Kelvin all the way up to 350 million Kelvin. In so doing, the core becomes as bright as the entire galaxy, which is pretty hard to comprehend or maybe even believe. But we don't see the star becoming that bright because in that short amount of time, the star can absorb this energy, so it's not seen as it actually takes place. But remember how I said that everything has its limits, and the degeneracy condition that we discussed actually has its limits as well. And this 350 million Kelvin is a temperature at which the degeneracy scenario is terminated. The safety valve begins to work again as the temperature beyond this causes an expansion of the core and subsequent cooling. So the core and the hydrogen shell around that little core expands and cools, decreasing the fusion rate. And it establishes a new equilibrium in the sun as the outer layers cool, collapse back in. The star shrinks. Actually, it becomes smaller, it becomes dimmer and hotter, at least on the external surface. So that helium flash is a dramatic, as I keep saying, turning point in what's going on with the sun. It turns out that if the masses are greater than 2 solar masses, then the helium will actually ignite before that degeneracy condition kicks in. You can achieve the 100 million Kelvin before degeneracy, and that significantly changes the way in which the subsequent evolution unfolds in the particular star. So we'll deal with that a little bit later. So the helium flash marks a change in the season of life for our giant star, our wonderful sun. Here's the helium flash. Subsequently, you notice the path on the HR diagram reveals that it's reducing in luminosity while it's rising in temperature. The core has heated to the point where the degenerate condition has been eliminated and it's now thermal again, so the core can expand and cool. But the helium has begun fusing. So we have a helium fusing core which produces carbon. So carbon is being built up here. And around this we have a hydrogen burning shell. So this is the new condition of fairly high stability that the star finds itself in. The helium flash is really a transition into a stable burning phase, a stable helium burning phase, but it's all at a lower luminosity, the horizontal giant branch phase. Even with both helium fusing and hydrogen fusing, you're still a little bit reduced in luminosity. So prior to that, we just had the furiously burning hydrogen shell. Now we have, without anything going on in the core itself, it was an inert helium core. Now you got helium fusion, hydrogen fusion, but it's all at a reduced rate down from the very dramatically high luminosity red giant just before the helium flash. Hopefully that makes some sense. So the track is moving down and to the left on the HR diagram.